Hello, this is the electrical engineering team from the Unmanned Ground and Aerial Vehicle System Showcase. My name is Alex Ondonov, and I'm joined by my teammates Isaiah Boone, Zachary Allison, Kelvin Meza, and Richard DiGiovanni. The goal of our project was to create a fully autonomous aerial and ground vehicle that worked together in tandem to create a series of challenges, also known as showcases. We worked in collaboration with the CSE and MAE sub-team, and we'll be showcasing our design in the annual competition hosted by the project sponsors, competing against various schools across Texas.
For the competition, there will be 3 challenges that the vehicles we have made will need to complete in order to earn points. For the first challenge, our aerial vehicle will start from a random spot on the UTA football field, and it will scout the field looking for a marker. Once it finds that marker, it will log its location and then land in a designated zone within 10 minutes to complete the challenge. For the second challenge, it's very similar to the first one, except that this time, once the aerial vehicle finds the location of the marker, it will communicate that location to the ground vehicle, in which the ground vehicle will then travel to that location and deliver a payload. For a third bonus challenge, this might include repeating challenge 2, except this time with a heavier payload.
To go over our system overview and architecture, both of our designs followed a very similar structure, with a battery that goes to power distribution board or boards that provide the correct power needed for each component. Some important components on each system that I wanted to point out were the navigation and flight controllers, which acted as the autonomous brain, or the brain for autonomy for both vehicles. The GPS, which was the main method used for the vehicles knowing their location and navigating, and the companion computers, which ran scripts created by the EE and CSE teams to control and facilitate the vehicle's operation. And lastly, the UAV's camera module, which was utilizing computer vision, is responsible for the Ariel marker detection.
For our experimental test plan, we tested all components individually to ensure they met power specs before integration. Then we measured the full system draw current using a current probe. The UAV drew a max of 58 amps and 829 watts, powered by a 4S 9000 milliamp hour battery. The UGV drew 24 amps and 353 watts with a 2S 8000 milliamp hour battery.
For our result, we have made strong progress towards testing key components independently. The UGV successfully used GPS to autonomously navigate to the delivery zone and complete a payload delivery. We tested this under various outdoor conditions, and the UGV consistently reached its target and delivered as expected. On the UAV side, we focused on autonomous vision and communication. And during manual flight, the UAV was able to detect our Ariel marker, send the coordinates to the UGV, and the UGV successfully completed the mission.
The process of building both vehicles was filled with many challenges. In the UGV and UAV system, some of these challenges include the payload design, cable management, and flight stability in windy conditions. Some key technical efforts involve scripting on the Raspberry Pi and fine-tuning PID controllers for both UAV and UGV to enable reliable autonomous performance. Both vehicles ran and completed various qualification tests and met sponsor requirements. The UAV and UGV are set to run autonomously in the Raytheon competition on April 12th.
We're good.
This is a video of our UGV completing its side of the mission. As you can see in the terminal screen, it's waiting for the UAV to connect and send it the delivery zone location. And in green, there it was. The delivery zone location was sent. Now the UGV is off on its mission. Incorrect landing zone to the left, which it did not navigate to, and it's navigating to the correct one to the right. We realized after the fact that the coordinates that we sent were actually slightly to the side, so it actually delivered much closer than it looked like in the video. In this video, we are testing the autonomous Ariel marker detection scripts created by the CSE team. Flying the drone manually 10 to 20 feet in the air, it could be seen that the Ariel marker is correctly ID'd. It was set that this one would be a non-drop zone, so it's printing non-drop zone detected in the terminal. This is a video of the UAV performing its scouting pattern that we decided, which is the snaking scouting pattern. UAV took off, and now it's following the path. You can see in the bottom left the path that was set in yellow, and purple is the path that it's following. Once it reaches the end, we had it set to return to home, so it returns to home. This test was performed in 15 to 25 mile per hour winds.